Now let us summarize all the different modes of convergence for the power series. To help us in this, we have the following theorem. For any power series, say of the form ck x minus a to the k from 0 to infinity, so that it's a power series centered at the point a with coefficients ck. So for any such power series, there are only the following possibilities in terms of convergence. So with regards to convergence, the first option is the series converges only at x equals a, and this was actually the case for the second series that we discussed. It only converged at one value of x. Secondly, can be the case that the series converges if absolute value x minus a is less than r for some positive r, and it is divergent for x minus a absolute value bigger than r. And finally, the third possibility is that this series converges for all values of x. 3 is it is convergent for all x on the number line. So as you can see, the picture here is more or less the following. We have a number line right? Then there is number a somewhere, and around this number a we have a neighborhood of radius r. So this would be a minus r, and this is a plus r. And our series, or this power series, is convergent here and divergent outside of this neighborhood. Okay, and so you can see that in the case 1, for the first case where it only converges at one point, we have that r is 0, right? So you can treat the first possibility in the same way if you think of it as neighborhood of radius r. So in case 2, it's clear what r is. This is r. And in case 3, r is plus infinity. So not only such r is defined in the second case naturally, we can also introduce the r is the radius of neighborhood in which our series converges for the two other cases. And so let us introduce some language for r. So r will be called the radius of convergence. And we will have another term, another related term. Let's say the set of x on which the series is convergent will be called the interval of convergence. As we have seen from the above, since there are only three possibilities in terms of convergence, the set always looks like an interval, except that this interval can be reduced to a single point, as it is in case 1, or the interval can be unbounded and comprise the entire number line. And so this will be called the interval of convergence. So whenever we say now to find the set of x's for which a series is convergent, we can just as well phrase it this way: find the interval of convergence of the power series. In the light of this theorem, let us recast the previous three examples that we discussed. So we have looked at several examples of series, and for each of these series we were able to determine the set of x's on which it converged. So let's say series, radius of convergence, and the interval of convergence. The first series we discussed was the sum for k from 0 to infinity, x to the power k. Right, and we saw that it converged precisely when absolute value of x was less than 1, or in other words, in the interval notation, this would be the open interval between -1 and 1. And so that meant that the radius of convergence in this case was 1, because this is an interval centered at 0 of radius 1. The second example we looked at was k factorial times x to k from 0 to infinity, and we saw that this series converged only at the single point, x equals 0, and so the radius of convergence here would be 0, because it's an interval centered at 0 of radius 0. It only includes one point. The next series that we discussed was the sum for k from 1 to infinity, x minus 3 to the k divided by k. We were able to determine that it converges for x's from the half open interval between 2 and 4. And so this corresponds to the radius of convergence of 1. This here is an interval centered at 3 of radius 1. And the last example that we discussed was the Bessel function. Let me just write J0. And so for J0, we found out that it converges for all x's, and therefore its radius of convergence is infinite. Now, there remains one other example in which the power series was equal to a polynomial. So I leave it as an exercise for you to determine what was the radius of convergence and the interval of convergence for that one series. It follows from this picture that the question of determining the interval of convergence, the set of all x's on which the series is convergent, boils down to determining two things: the radius of convergence and the behavior of the series at the endpoints of the interval of convergence. How is this done in generally? Well, there are two things to remember. So to determine the interval of convergence, the first thing to do would be to apply the ratio test in order to find R. R is obtained from the ratio test. And then, once you know R, you will want to inspect the endpoints for convergence. So let us illustrate this by an example.